All right, let's wrap up Unit 7 as we talk about the side splitter theorem and other triangle proportionality theorems that we can use as we uh, look to find similar triangles and apply that property of proportional sides and congruent angles within triangles. So let's first take a look at the side splitter theorem, and it's also known as can be talked about as we talk about a triangle. It's proportionally cut by a parallel line. It splits sides in half. That's why it's known as the better name as side splitter. So let's take a look at that on GeoGebra. There's a link on the website if you're interested in checking it out on your own as well. So here we have a triangle. It's cut by a parallel line. Remember that the triangle mid-segment theorem. So let's say D and E were midpoints. We would know that it would be split into proportional parts. And if this isn't a midpoint, if it's a different point, if I can get this to move, so it's further closer to A than it is to B, and E is closer to A than to C. Let's just take a look at the measurements. So in this particular triangle, as we compare, it still looks like a dilation. And we know this angle is going to be same angle A in both triangles, the small one and the big one. So we just need sides to be proportional. And if this is a parallel line, well, what are we going to have? We're going to have this angle the same as this one because we have corresponding angles. And E and C will be congruent because they're corresponding angles as well if these two lines are parallel. So since we have angle-angle similarity, we know that the triangle side lengths will be proportional as well. And you can see that as we move this triangle around. It doesn't matter the shape of it. But AD is 3.46 to DB 8.78, which is a ratio of 0.39. AE, which is 3.3 to AC, which is 8.37, is also a ratio of 0.39. Notice we can also match up these corresponding parts. Well, AD, so the sides that are split, that's kind of why it's known as the side splitter theorem. So it splits the sides into proportions as well. So 3.46 to DB, which is 8.78. Actually, that's the ratio I just showed you, wasn't it? But it also has the ratio of the full triangle, so 3.46 to the full length of 12.24. Same with AE to the full length AC. That's proportional as well because it's a dilation. And then the sides are split into proportions as well. And it doesn't matter if I change the points. As long as the two lines are parallel, the sides get split into an equal ratio. And triangle side lengths. So either one works. Okay. So that is the side splitter theorem when we have a proportional line. So let's put that information down in our notes. That's one of the triangle proportionality theorems. If a line is parallel to one side of a triangle and intersects the other two sides, it divides the two sides proportionally. Whoops, let me get my pen here. So if TU is parallel to QS, then what do we know? We know the two sides are proportional. If these two lines are parallel, then we know RT to TQ. So that side gets split proportionally the same way that RU to US. So in the same way, the converse of that, if two sides are split proportionally, then it's parallel to the third side. So if RT is proportional to TQ in the same way that RU is proportional to US, then TU would be parallel to QS. So this is our side splitter theorem right here. Okay, so let's apply that side splitter theorem. QS is parallel to UT, RS is 4, ST is 6, QU is 9, find the length of RQ. So see if you can do that with these and determine if PS is parallel to QR. Restart the video when you're ready to check your answers. All right, so since this is the side splitter theorem, two lines are parallel. I can match up the sides, should be proportional, so 4 to 6, same way that x goes to 9. Solve that proportion. I have 6x equals 36, x equals 6, so RQ is a length of 6. Do the same with YZ here since the two lines are parallel. Sides get split proportionally, so 44 to 35, in the same way 36 to y. Cross products, I get 44y equals 1260. Divided by 44, I get 28.63 repeating. Okay. Now, determine whether PS is parallel to QR. In order to determine that, the sides would need to be split proportionally. So I match up 90 to 50, 72 to 40. I can divide 90 and 50 by 10 to get 9/5. 72 and 40 can both be divided by 8 to also get 9/5. So since they have the same ratio, we can say that the lines are parallel. Okay. Next one we want to take a look at is when we have three parallel lines intersected by two transversals. So it's similar to that side splitter, except we don't quite have the full triangle yet. But we have three parallel lines cut by two transversals. They're going to divide the transversals proportionally as well. And you can kind of picture that that's the same as that side splitter theorem. So if we take a look at our example here, UW to WY in the same way that VX to XZ. That same concept applies there. Now we're going to take a look at this next one, when a ray bisects an angle of a triangle. Take a look at that one in GeoGebra as well. So as we take a look at that, we have a ray bisecting an angle. So angle BAC here is bisected. Take a look at the side lengths of the triangles. And now we're going to compare the ratios. So the ratio of BE to AB is 0.72, and CE to AC is also 0.72. And if I change this triangle, notice the ratios stay constant. They're going to be in the same ratio of these two angles when I have an angle bisector. And you might be wondering, well, why does it work that way? Well, here's a proof that kind of explains that, and it actually does explain it. We have this angle bisector, so we want to prove that BD to DC is the same as AB to AC. So we had the ratio a different way, but it doesn't matter. We're using the same, I could say BD to AB, just flip that sideways, but it's the same ratio, same proportion. So in order to do that, we draw a line BE parallel to AD. Okay, so I draw an extra line in here parallel to that angle bisector. We're going to extend CA down to meet BE at point E. So by the side splitter theorem, we know that CD to DB is the same proportion as CA to AE. Okay, we just talked about that. So that would make angles 1 and 4 corresponding angles because these lines are parallel. Okay, so since these lines are parallel, 1 and 4 are corresponding angles, and those angles are going to be congruent. And since AD is the angle bisector of CAB, 1 and 2 are congruent as well. And since this line is parallel, these two lines are parallel, AD and EB. AB is a transversal, so 2 and 3 are also congruent by the alternate interior angle theorem. So by the transitive property, 1 is the same as 2, 2 is the same as 3, 3 is the same as 4. We can say 4 and 3 are the same angle. And since they're the same angle, we know that this would be an isosceles triangle. Base angles are congruent, opposite sides are congruent. So now we can take out AE and put AB into the equation, or into the proportion, because those are the same. And there goes my drawings. As we scroll down here, where was I? Okay, so here we have this final proportion. So hopefully that makes sense. So since we have all these angles are the same, when we drew in this extra line, typically the side splitter theorem, we'd have CD proportional to DB and AC proportional to AE. And since we proved that this line, AE, is the same as AB, we just have that same proportion, CD to DB is the same ratio as CA to AB. Okay, so that's how that one works. We'll apply that in our work here. If I can pull up the notes again. There we go. So if a ray bisects an angle of a triangle, where can I put my face? Up here. Divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides. So in our case here, AD to DB is the same as AC to BC. And now let's take a look at how we apply that in some examples. So in our diagram here, angle 1, 2, and 3 are all congruent. GF is 120 yards, DE is 150, and CD is 300. Find the distance HF between Main Street and South Main Street. So why don't you work to solve that one, and then when you're done with that, take a look at the diagram below. QPR is congruent to RPS. Find the length of RS. This one down here. Restart the video when you're ready. All right, so as we set up our proportion here, we have three parallel lines. Since all three angles are congruent, corresponding angles are congruent, the lines are parallel. If lines are parallel, we got these transversals cutting through here, which means these are all cut in the same proportion. So 150 to 300, same proportion as 120 to X. We can see that it's doubled, so X will be 240 for GH. If I want to find HF, that's the full length, so 240 plus 120 is 360 yards. Bottom one is that angle bisector, splitting angle QPS onto two equal parts. So QR to RS in the same way that QP is proportional to PS. So here's my proportion with that. Cross products, so 7x equals 13 times the quantity 15 minus x. I distribute. 195 minus 13x, add 13x to both sides. 20x is 195, divide both sides by 20, and I get x equals 9.75. X was the length for RS, so RS is 9.75. So today we looked at a couple different triangle proportionality theorems. The side splitter theorem, if we have two parallel lines, the sides are split proportionally. Converse of that, if sides are split proportionally, the lines are parallel to each other. And then we took a look at, if we have three parallel lines intersected by two transversals, those are proportional. And the angle bisector, we have proportional parts in that triangle. So do the work. If you have questions, let me know in class.